Oh my god.
For better, for worse, for richer, for poorer, in sickness and in health, to love and to cherish, till death do them part. Physics and graphs are inseparable. And for obvious reasons, graphs allow the physicists to see trends between two variables and come to a conclusion.
I haven't a clue what's going on here, but I'll act like I do.
So, this video will go through how physicists will use graphs in their labs. It'll help you a lot with CSEC, right? Here's a table I stole from my friend on the date of October 12, 2019 because I didn't actually do the lab myself. We were trying to determine the spring constant of a spring. Now, about 300 years ago, this shriveled Hasbro looking mother named Hooke made the equation F is equal to KE. He said the more force on a spring, the more the spring will extend. And the amount the spring extends by, if you multiply it by a measurable constant, that'll give you the force that you applied to said spring. So how does my experiment prove this? How does my friend's experiment prove this? We just need to keep adding increasing force and measure how much longer the spring gets. So let's do that. To get a larger force on a spring, we just use gravity. So to use gravity, just need to put bigger mass, right? So we added a 50-gram mass, measured the extension in centimeters, added more mass, measured the extension in centimeters, added more mass, measured the extension in centimeters, added more mass, measured the extension in centimeters, and eventually we got this table that I stole from my friend. Weight / force would be mass times 10. We're using gravitational acceleration as 10. So that's where we're getting the N Newton values from. And of course we want to work in SI units. So that's why we'll make a kilogram table, world column, and a meter column. So now that we have all the values for the table, she plots a graph of force versus extension. Force is on the y-axis and extension is on the x-axis. Force is measured in newtons and extension is measured in meters. You always need to formulate a scale for each axis. So in this graph, this is what the scale will be. The y-axis will have 2 centimeters for 1 newton, and the x-axis, as you can see there, has 2 centimeters for 0.02 meters. So that's the scale we're using. On the table, we had corresponding weight values and extension values. So those corresponding values will make the coordinates that we use to plot the points. So eventually we'll get some points. And what we're going to do is that we're going to draw a best fit line through those points. Now a best fit line should be equally as far from each point as possible. In this graph, the points are good boys and they will line up almost perfectly. In other graphs, you'll have to draw a line between all the points, giving them equal distance. And even in other graphs, you might have to draw a curve, right? So it depends on the graph you get. Now, the best fit line, you have two useful pieces of information that you can gather. You can either get the gradient of your line, or you can measure the area under your graph. Now, in this experiment, we don't need to care about the area, but the gradient of the graph of the best fit line, that'll be very useful. So, how do we find gradient? We have two ways. We have the formula m, which is gradient, is equal to y2 minus y1 over x2 minus x1, or you can use the concept of rise over run. Now, I'll show you both, right? They're both situational, depends on the information that you are given. Nice. So let's use rise over run first. Now, the first step in getting gradient, in both methods, rise over run and the equation, is selecting 2 points on their line. Not the points that you plotted, the points on the best fit line, okay? Using the line. So if I want 2 nice points on this line, right now I'm thinking of using this point right here. What's the coordinates to that point? Write them down. The coordinates are 0.02 and 1. Right, so the coordinate 0.02, comma, and 1. So you have the coordinates for this point right here. Write them down. Nice. Next, choose the next coordinate. I'll go higher up, and I'll take this point right here. So this is, what's the coordinates for that? that is 0.06 for the x value and 3 for the y value. So you have 0.021 and we have 0.026. So write them down somewhere. Type it on our laptop or join our laptop so it wouldn't look as good. Right? 0.06 and 3 and 0.02 and 1. Nice. For rise and run, you don't actually need those coordinates. Right? You just need to know where they are. So, you choose a direction and you just go in that direction. So using rise over run, I decide that I want to go from this point right here, 0.021, that's the coordinate, but I'll call it coordinate A. I want to go from coordinate A all the way to coordinate B. Right? And I just need to record the actions I take to get there. So, my run, your run is the X direction, your rise is the Y direction. So, my run to get to B in the X direction, well, how much spaces do I need to move? I need to move 1, 2, 3, 4. 4 pieces and I land right here. Now, remember to look at your scale. In this graph, it's 4 centimeters, but in reality, that'd be 0.04 units. 0.02 minus 0.06, you get 0.04, right? Each centimeter is 0.01, so you end up with 0.04 in total. Then to go up, how much coordinates do I need to go up by to get to my B value, right? Well, my rise now, start with my run. Now my rise would be 1, 2, 3, 4. Right, that's my rise. 4 pieces. However, what's the scale right here? If you look at the scale, is it starts from 1 and we end up on 3. So difference between that'll be 2, right? And this scale, 1 centimeter is 0.5. So if I go up 4 times, in total I went up twice in terms of units and the scale. So my rise was 2 and my run was 0.04. Good. Now I just work it out. So rise over run, rise over the run. And next thing you need to notice as well, I went for my rise, I went upwards. For my run, I went to the right direction. Those are the positive values. Going towards the right is always positive, and going up is always positive. Okay, so we end up with 0.04 under 2. And if you work that out in your calculator, you will end up with 50. And yes, that is the gradient of this graph, 50. And we use the rise over run. Now let's do it using the equation. So the equation is y2 minus y1 over x2 minus x1. So you'll just look at this and choose which of these coordinates you want to be your 2 values. So this right here, these are the bigger numbers. I'll make those my 2 values. So if these are my 2 values, this 0.06 right here, this will be x2. And this 3 right here, this is my 2 coordinate, right? So this 3 will be y2. And if this is my 2 coordinate, this will be my 1 coordinate. And obviously that means that this 0.02, this is x1, and the 1 value, that is my y1. And now you just put them into the equation. So just slot them into the spots that they need to go. Which means that I have 0. Well, no, y is on top. Good. So I'll have y2, that's 3, minus y1, which is 1, over x2. What's x2? x2 is 0.06 minus x1. What was x1? x1 was 0.02. And you'll get the exact same thing, right? Rise over run is just more useful when you have like a graph right there and you could see it clearly. I could just do it in your head with rise over run, kinda. But the equation, that's for more complex numbers. So when you work this out, up on top here you'll get 2, below here you'll get the same 0.04, and you'll put 15 newtons. And that's how, my friends, that's how you find gradient. Using rise over run or using the equation itself. Now, of course, gradients can be negative. So let's go to an example where the gradient is negative. And we'll use rise over run. Now, I want to figure out the gradient of this. I'm going to use rise over run. And there they have two nice points. I'll call this point A. And I'll call this point B. And I just want to figure out how do I move to get to point B. So first of all, for A to get to point B, I need to go 2 paces to the right. So that's the run. The run is 2. Now it's rise over run, so 2 will come at the bottom. And then to get to B, I need to go downwards. And how much paces downward do I need to go? I need to go 6 paces downward. And since it's 6 paces downward will be negative. Therefore, it'll be negative 6 on top. That'll be the rise. Because it wasn't actually a rise, it was more like a fall. But then kush. Nice. So, minus 6 divided by 2, that's minus 3. So this gradient is minus 3. And that's using rise over run, it's easy to see. Minus 3, right? But let's say using the equation. Let's make these the 2 values. Let's make these the 1 values. Where they have the coordinates right there. So this is x2. This is y2. So y2 is 4. So 4 will come here. Remember, y2 minus y1. So this minus sign also has to come. No matter what, right? And what's x2? x2 is minus 1. So this will be minus 1. And you have to put minus afterwards. Because remember, that's part of the equation. x2 minus x1. So you have to have this minus sign here no matter what. And now what is x1? x1 is just 1. And what is y1? This is y1. y1 is minus 2. So put it in brackets, put it right there. And then you work it out. What will we get? So minus times a minus is a positive. 4 plus 2 is 6. And a minus 1, that'll be minus 2. Right? Make sure you note that. 6 divided by minus 2, that'll give you minus 3. So we get the same thing, right? A negative gradient. So now you know how to get gradients in your physics graphs, any graph really. Nice. And that'll be it for this whole example with the Hooke's law. We got the gradient of the graph, we got 50. So that means the constant for Hooke's law was 50 newtons. That was the spring constant of the spring. But in other labs, other graphs, other scenarios, you might need to get the area under of a graph. For example, if we're doing a velocity time graph, you'll need to get the area under the graph to give you distance. So, let's calculate distance for this graph right here. How do I get the area under this graph though? Just split up the shape that we have with the graph into shapes that you know the area of, then work it out. So this could be a triangle. This right here, split into the easiest shapes you could. This could be a next triangle. And this will turn out to be a square. And then I have a triangle here. So I have 4 shapes I need to get the area of and add them together. So what's the area of this triangle? Area for a triangle, base by height, divided by 2. So the base is 4, height is 3, 4 times 3 is 12, divided by 2, that'll be 6. So far we know we have 6 in the block. So 6 in the chamber. Then you have a square right here. This square is 1, 2, 3. So 3 by 3, that'll be 9. Nice. Next we have this triangle. So base by height, the base is 1, 2, 3. And the height is 1, 2, 3, 4, 5, 6. I don't know what to count, so I'm going to make sure. 1, 2, 3, 4, 5, 6. Yes. So 3 by 6, that's 18. But you divide it by 2 because it's a triangle. So that'll be 9. And then this triangle right here. This is 1, 2, 3 times 1. So that should be 3. But no, wait. I need to divide by 2. So 3 times 1 divided by 2, that'll be 1.5. So when I add all of this together, 9 plus 9 is 18. 18 plus 6 is 24. 24 plus 1.5, that'll be 25.5. So the area under this graph is 25.5. And the area under a graph, well, area under a graph of velocity versus time is the distance. That's what the area is. Okay, right here. So this distance is 25.5 meters. Right, that's the total distance traveled through this entire experimental graph catching data right there. And my friends, with all of this done, you know how to use graphs in physics. You can be married, interweb, cling together forever with physics and graphs there. Because you know how to do it now. You know how to finish your labs, you know how to do everything. So go out in the world and partake in this beautiful tool of graphs. Now for the mathematician, they'll have a little bit more stuff they need to know. But for now, with physics, this is all you need to do. Faces and graphs and key graphs, to be honest. So enjoy that. I'll make the mathematic video later on. There, learn about midpoints and length and parallel lines and perpendicular lines and etc. So bye.